Good afternoon, everybody. So, continuing with the algorithms regarding the problems solving of STL files. So, today, what we are going to look into are two of the most common problems that are encountered in an STL file, that is the degeneracy and overlap. And we are going to see how this problems of degeneracy and overlapping are basically solved using algorithms and what is the basis of algorithm. Now, generally what happens in STL file is when you have an STL file, you generally get an object like this. You generally get an object like this where you have one facet. This is, let us call it as facet A, and this is called as the facet B. So there are two facets which are sharing a common edge. The problem that encountered over here is that if this edge becomes straight, and if by some means it also incorporates another vertex also, then this line AEC, this line of vertex A, vertex E, and vertex C basically becomes a straight line, and it basically generates degeneracy into the system. So degeneracy is something that is not desired, because what happens is, because of degeneracy you start to get more gaps in the STL file, and again filling of the gaps takes the maximum amount of time to recover. So solving this problem of degeneracy is very important, and the most common algorithm which is utilized over here to solve the problem of degeneracy basically uses the vector algebra. So how do we solve this problem is that we have two facets. We have two facets, facet A and facet B. So this is facet A and this is your facet B. Now this is A and this is C, this is D, and this is B. So now what we do is the edge AC, that is the common edge between the two facets, that is converted into vectors. So AC is equal to C vector minus A vector. That is what we already know. Now, in order to check for collinearity, whether the two vectors are collinear or not, what we do is we take two vectors x and y, where x represents AC, that is the complete common edge, and y basically represents a new added vertex, along that line AC. The vertex has to be placed on this line, that is the shared edge, and the area, that the line, that is EC or CE, is now utilized. Now, in order to define these two vertices, what we define is AC is equal to xi plus x2j plus x3k, and y is equal to CE, that is y1i and y2j plus y3k. So what we are trying to define over here is AC in the vector form and CE in the vector form. Now, in vector algebra, the collinearity definition of collinearity is given as the vectors multiplied by constants, that is the scalar constants, and both the scalar constants, that is x, s, and t, they should be non-zero. So by mathematical definition, what we do is we multiply these two vectors with these two non-scalar numbers, and if this value comes out to be zero, the multiplication of a vector with a non-scalar and their additions, if it comes out to be zero, then these two vectors are collinear. But what happens is, when you start to apply this equation in an algorithm, definitely you need to give some sort of a tolerance. Because these values will not come out to be exactly zero. So what happens is we define a predefined tolerance. We give a predefined tolerance. Generally this value is given as 0.025. The unit is by default mm. The unit is by default mm. This value of epsilon is actually a user defined value. It is a user defined value, and these values are actually inputted during the algorithm itself. Now if this value falls be- below the threshold limit, then these two vectors, that is AC and EC, are considered to be collinear. So these values are going to be defined by the user, and generally this value is 0.025, and the maximum value generally that is given is 0.050, but still you can give as much value as you want, whatever value you feel like, depending upon the type of vector you are using. So once you have identified and defined the value of epsilon, you have found that the two vectors, that is the vector x and the vector y, are collinear vectors. Then the position of E has to be generated. The position of E has to be generated. That means this E is now going to be defined as a permanent vertex. This E becomes a permanent vertex. So now on this line AC, you have identified a new vertex E. You have identified a new vertex E. Now what happens is this facet A is going to be divided into two facets. So what you do is you simply join DE, and what happens is the facet that was already there, that is the facet A, is now broken up into two facets, that is facet A1 and facet A2. So this whole facet is now going to be divided into two facets, that is facet A1 and facet A2. So the vertices of those facets are again defined. So the for this facet the vertices are A, D and E, and for this facet the vertices are E, D and C. So now what has happened is a single facet has been divided into two facets, thereby eliminating the problem of degeneracy. Now once you have identified or broken up the facet, you have broken up the facet into two facets. So now what you do is in the original file you locate the location of the facet A, and remove this information and store the information of facet A1 and facet A2, which basically removes any degeneracy which is developing into the system. So how do you remove degeneracy, to be very in a very generic sense? So how do you remove degeneracy? You simply remove degeneracy by adding a new vertex, and creating new facets. That is adding vertex and creating new facets. So the removal of degeneracy can be done by adding a new vertex and by creating a new facet. So this checking for of vector algebra is basically done for all the facets. It is going to be done for all the facets, and wherever this condition is not satisfied, there that problem of degeneracy is said to be eliminating. The problem of degeneracy is said to be eliminating. Secondly, for one single part or one single STL file, the value of S and T are going to be constant. The value of S and T are going to be constant, and that is to be again defined by the user. That is again to be defined by the user. So you cannot go on changing the value of SNT for each and every facet, because if you start doing that, then you might be having like 10 to 15,000 facets. So deciding 10 to 15,000 values of SNT will become very difficult for a user, and the time taken for elimination will be huge. So the value of SNT is defined by the user at the initial stage itself, and the value of the epsilon, that is the tolerance, The value of the tolerance is also defined by the user at the initial stage itself, and based on that, the problem of degeneracy is going to be solved. Now, the second problem that we generally observe in this system is basically what we call as the overlapping facets. The problem of overlapping facets. Now, how does this overlapping facet actually look like is that the vertex actually has stretched to different dimensions during the STL file because of the rounding of errors, rounding of errors. And as a result, what has happened is the location of the vertex has changed. As a result, the edges are basically overlapping each other. So again, here what, as I said, what happens is the condition of overlapping actually is caused by the errors which are introduced during the inconsistent numerical round off. So what happens is 4.667 actually remains the same, but 4.759 becomes 5. Similarly, 4.016 becomes 4. So what if this condition happens, then you get a gap, and if this condition happens, then you start to observe overlappings. So in order to eliminate this overlapping, it is pretty simple to do that. So what we do is we basically go for vertex matching. We go for vertex merging. So what is vertex merging over here? Basically, vertex merging is nothing but defining a proper round of error value. Defining a proper round of error value. That means anything which is greater than 4.5. If the value of x is greater than 4.5, it will be taken as it will be taken as 5. If the value of x is less than 4.5, it will be taken as 4. So when this thing starts to happen, you generally get a whole number. You generally get a whole number that is either 4 or 5. So that prevents any overlapping happening in the STL files and the facets also. So how do we do convert this thing? So first of all, what we do is we start with a predefined numerical round of tolerance. We start with a predefined numerical round of tolerance. So generally, what mathematics basically tells me was what, as I explained you earlier, that anything which is less than 4.5, if x is less than 4.5, then it is equal to 4, and if x is greater than 4.5, then it is 5. This is according to mathematics, but what people generally do in this algorithm is they define actually four different stages. If x is greater than 4.01, but sorry, if x is greater than 4.01 but less than 4.25 or equal to 4.25, in that case the value is taken as 4.25. If x lies between 4.26 but less than equal to 4.5, then it is 4.5. Similarly, if x is greater than 4.5 but less than equal to 4.75, then we take 4.75. And if x is greater than 4.75 but less than equal to 5, then x is equal to 5. So these are the general values that we take in terms of this rounding off. And the tolerance value that we have defined over here is 0.25. The tolerance value that we are defining over here, the tolerance value that we are defining over here is 0.25. Now, it is very much recommended, because it is very much recommended that this merging of vertices has to be done before you start looking for gaps. Because what happens is, if you have already filled the vertices, already filled the gaps, and then you go for vertex merging, new gaps may appear on the surface. So in order to prevent that, it is always recommended that this merging of the vertices has to be done or should be done before the gaps have been identified and filled on the surfaces. Because this also helps to identify if there is any error in the edges, if there is any error in the edges, and also it helps us to identify if there is any degeneracy which is occurring before the facet has been filled up, before the empty facets have been filled up. So the checking of edges orientation, the checking of edges orientations, and the degeneracy should be done before you fill up any of the gaps. So this is all about today's lecture that I wanted to complete.